everyone, my name is Mark Zlamal. Welcome to my technical retrospective on a lighting project that I built to complement our new IKEA PAX closet. In this video, I'll cover my technical journey that includes the circuitry, the integration points, the challenges that I faced, and the final results. I don't have a before picture, so this is a typical closet system that is offered by IKEA. This sample design has two full-sized closet units in the center and two half units on each end. For lighting, my objective was to build a modern LED system from scratch that is extensible and driven by software. Here's my after picture with all the lighting installed. Notice we have a 4-piece PAX solution. 3 units are full-size double-door closets, and the far right unit is a half-sized single-door closet. Each closet is equipped with its own independent light strips. My goal was not to reduce costs. In fact, the cost to kick off this project was far from modest. This was a personal challenge to satisfy my electrical engineering interests. I could have purchased a few of these standard IKEA light bars. The units aren't bad. In fact, they're stylish, have a built-in optical sensor to illuminate when a door has been opened. My problem is that I simply don't like them. The bars are too short, the color temperatures are limited, and the LEDs are spaced far apart, meaning they're not as bright as I hoped for. The LED strips I used in this project are manufactured by a company named Inspired LED and are classified as mega bright, so they are some of the densest strips at 36 LEDs per foot. I ordered these as a 12-meter ribbon, along with all my supporting electronics, online through Mouser. I've recently discovered the world of IKEA hacks and the communities that explore all the creativity behind it. Most hacks focus on the physical repurposing of the materials or redesigning furniture. And this is great, but I found a few that augmented the furniture by introducing technology to make it more versatile. And this was actually the basis for my motivation on this project. So let's jump into the details. Here's a view of my lab. A bit cluttered, and it gets quickly messy, especially when my kids play with the equipment. Here I do my prototyping and breadboarding, which allows for rapid engineering with little to no constraint. I purchased a few Arduino Uno boards. These are the brains behind the light control. The board handles fancy dimming effects, listens to inputs, and I even implemented auto shut-off logic if a door is left open for too long. This is very easy to do with the Arduino development environment. This is a free download. Included is an extensive collection of sample projects to get started quickly. It also lets me modify and burn programs to the chip very quickly as well. The full project consists of the Arduino board at the left that controls the system. There's a two-way communication from here to the rest of the system. On the right side, we have a driver circuit that controls the brightness of the strips. The Arduino generates a pulse width modulation signal, also known as PWM, to govern the LED brightness. The driver board uses MOSFETs to drive current through inductors connected in series with the LED strips. And here's actually where I ran into my first problem. PWM signals and inductors cause significant noise in the entire circuit. My first attempt fried the Arduino controller. While I strive to be well within electrical characteristics, a direct connection created sufficient interference that exceeded the pin maximum ratings of the Arduino. I chose to isolate the controller circuit with the driver circuit using optocouplers, and that's the purpose of the interface board in the middle. We're now using light as a means to electrically isolate the system while still maintaining communication between each component. And this is actually what drove my interest in this project. It's the optical nature of it. I use the light sensors to check whether a door is open or closed. I leveraged optocouplers to protect my controller from the LED drivers. And light was the resultant product of this project. So the software tools that help me here are the Express PCB and Express SCH products. These are also free downloads. After a few iterations of experiments and some trial and error, here are the simplified schematics. The circuit diagram highlights all the components that implement sensing and communication. At the top left, output from the controller. The Arduino produces a PWM signal that is sent to the opto-isolator. The right side is fed to a transistor that drives a MOSFET to power the LEDs. On the right side, input to the controller is here to sense if a door is ajar. I used optical reflective sensors to check the doors. Our closet has 1 and 2 door variants, so for single door closets, the system is trivial. The light turns on when I open the door. For closets with double doors, I need to ensure that the light turns on when at least a single door is opened. That's the basis for the bottom circuit. I have 2 inputs that are logically ORed with the use of transistors. I duplicated all these circuits 4 times, essentially 1 channel for each closet. We have 3 double door circuits and 1 single door variant. After reviewing the schematics again, I played with the PCB layouts and printed them on a laser printer. This gave me a cool looking mask that I was able to trim and iron on directly onto a copper clad board for etching. There's actually quite a few YouTube channels and guides on how to accomplish this. It's the classic toner transfer method, and results are often varied. In my case, here's the end result after etching. It's a little rough, but good enough for the prototype. Next, I soldered all the parts onto the board, and here's the end result. I don't actually have any videos of the soldering process, but there's nothing really that exciting there. I do prefer to use surface mount components over the through-hole devices. I don't really enjoy drilling thin little holes. I just find it a lot easier to position the components using tweezers. The left-hand side is the MOSFET driver board with the inductors. During testing, I noticed that the inductors generate a humming noise when the lights are on, and this was actually my second problem. When the lights are on, it was way too loud for my satisfaction, so I used hot glue to cover the inductors and muffle the noise. The interface board has headers that allow me to connect it directly to the headers of the Arduino board. For these devices to interface nicely, we're talking 0.5 millimeter tolerances to have nice, clean, proper connections. So when they say measure twice, cut once, I probably measured 10 times and drilled once. The wires from the interface board are then connected to the driver board. I did nothing fancy on this front because I was eager to get the project completed. And there's nothing fancy at this point. Installation, pretty straightforward. I have a few inches of clearance at the top of the closet to store all the electronics, the power cube, and all the wiring. This is the very top of the closet. Optical sensors were hot glued to the top of the unit. Wires running upwards to the rest of the system. This is the first time I'm using these sensors. They're actually very clever. The emitter and detector are divided by a barrier, and the optics are angled inward slightly. This design allows for a specific optimal working distance, and in my case, the sensor works best for gaps in the 7 to 15 millimeter range. When the lights are on, the result is enlightening. The cameras doesn't do justice. As the lights turn on, the camera's digital shutter starts to autocorrect and starts to flicker, which is too bad. It looks much better in person. So what did I learn from this project? A, even the simplest circuits turn into complex problems when you factor in mechanical situations, such as the optical sensors and even the inductors to a certain degree. Installation is equally as hard as circuit design, and it's virtually impossible to perfect. It's hard to hide wiring and to mask things and to cover up to make a nice looking panel and everything else. So we're near the end. I never really discussed the driver circuitry. That's an easy one. I used IRF 540 MOSFETs, and they're driven with transistors, general purpose transistors. There are plenty of designs online to best apply these components. I probably could have gone deeper into the details, but then that would take away from your experimenting, right? Well, thank you. I hope you enjoyed this video. Thank you for watching. Bye-bye.